So, hopefully you've gotten all of your great ideas on that previously phenomenally excellent talk written down or tweeted or up on the wall of ideas. And I'd like to take you now on another kind of journey and maybe try and change your perspective a bit. So humans have been on a journey to understand who we are, where we came from, what is, what should be, and of course, we've wondered whether anybody else is out there. And that journey is at a particular point, here and now. But we have to think about what we really mean by here and now. So here, okay, we're all sitting in this wonderful facility, and we now know with all of our great devices, personal electronic devices, and Google Earth, that we can perceive that we're actually here in a larger context. And in another context, from the altitude of low Earth observing satellites, we are pretty comfortable with understanding that we're here. Since 1968, when Bill Anders snapped this Earthrise picture as he was coming around the limb of the moon, we've begun to understand that we are a planetary society, somewhat isolated in space. So we're here. When the Cassini spacecraft went into orbit around Saturn, it looked back through the rings. And I don't know if you see that little white dot that the arrow's pointing at, but that's here. And the Voyager 1 spacecraft in 1980, as it was heading out of the solar system, it turned around and took a picture of us in the zodiacal light here and gave us the understanding of the pale blue dot. We're actually here in the boondocks of a very beautiful spiral galaxy, which if we could get outside and look back, would look something like this. And we are recently getting comfortable with the idea that that galaxy is here in this larger cosmic context. But what about now? All right? Now, it's the second millennium, the 13th year, the 6th month, the 5th day, the 13th hour, and I had to figure out what it might be, the 30th minute and counting. That's what we usually think of now. But actually now is in the very last instance of a 4.5 billion year history of the planet Earth. And you can see that we're beginning to strain our graphical capabilities of seeing the big and the small. We've occupied such a very short temporal piece of this long history. And you need to go back farther than that. And now, right, is the current epoch of a universe that started with a Big Bang some 13.798 plus or minus 0.032 billion years ago. So this is the context of our now. And our journey has brought us to this current place where we understand that our sun is one of 400 billion other stars in the Milky Way galaxy that's 10 billion years old, and our galaxy is one of 100 billion galaxies in a cosmos that is almost 14 billion years on from a Big Bang when the cosmos and time itself got started. And what we need to do to go beyond what Salim was talking about in a planetary context, is to appreciate that our here and our now are in a cosmic context, and we have an intimate connection with that cosmos. We are, literally, all of us, what happens when primordial mixtures of hydrogen and helium evolve for so long that they begin to ask where they came from. The iron in the hemoglobin molecules in your blood were manufactured, were fused deep within the heart of a massive star that exploded billions of years ago, leaving remnants such as this modern example, which have been and are continuing to be incorporated into new generations of stars and of planets and perhaps other life. So those of us in this room are incredibly privileged for many reasons. But I think intellectually we're incredibly privileged to begin to understand our here and now as being part of a fragile island of life in a universe that is full of possibilities. And so I think we can get over some of the difficulties that Salim was alluding to if we expand our context, our perspective, to acknowledge this universe and the possibilities out there. Certainly, extremophiles, organisms that live in environments that are sometimes extremely mineral rich, but certainly hazardous to human life. These extremophiles over the last few decades have been allowing us to think about life in other environments. They are motivating us to think that perhaps there's a lot more habitable real estate out there in the cosmos than we might once have thought. One of those habitable environments might be this cold desert, which isn't in Southern California, although it looks very much like the Mojave. This is the desert of Mars, up close and personal, as brought to us by the Curiosity rover. And Curiosity doesn't have the capability to detect life, but what it can perhaps do, and is beginning to do, is to detect the conditions that might have made life possible in the past, or perhaps still today. Extant life in some buried liquid aquifer on that planet. And if life has never existed or doesn't exist today on Mars, we can look farther in our solar system to the giant moons of Jupiter and Saturn, where beneath the icy outer crusts, we believe there are large liquid water oceans that have been there for 4.5 billion years. There's some indication that life on this planet began in an ocean billions of years ago. Perhaps life exists on these oceans within our solar system. And a second genesis of life discovered within this one small solar system would mean that Christian de Duve, a Nobel laureate who died recently, was correct when he said life is a cosmic imperative. He had a beautiful Belgian accent and always said, oh, you want to just say, yeah, this is, I believe. It's kind of scientific religion. When he says something like that, you say, yeah, it's got to be, but we don't know. It's possible, but we haven't decided or found evidence that habitable and inhabited exist beyond this planet. Okay, what about beyond our own solar system? Well, until 1995, we actually didn't know whether planets existed around other stars like our own sun. Since then, we've found thousands of exoplanets and exoplanet candidates. And this particular spacecraft, Kepler, has been designed with the specific job of finding Earth-sized planets in the appropriate orbit around their stars where there might be liquid water on the surface, the so-called Goldilocks planets. And it does it by staring at 100 square degrees on the sky, those 42 little rectangles. Kepler has a 93 megapixel camera, CCD camera, a fancy example of the kind of thing that's in your cell phone. And Kepler stares at 173,000 of these stars continuously, waiting for one of those stars to blink. Why might it blink? It might blink because, the movie didn't play. All right. It might blink because a planet transits in front of the star, blocking a small bit of light. A part in 100,000 if you're talking about the Earth going in front of the sun. And although Kepler may be, sadly, at the end of its operational phase, it has proven extraordinarily successful to date. And we know, so now I'm, well, let's see, we do it again. No. Can you advance to the next slide and we'll get out of this technical? All right, so it works. All right, some of those stars do blink. 2,740 stars or planetary candidates have been found around those 170,000 stars, and 105 have so far been confirmed from ground-based searches. And indeed, something like 58 of them represent stars with planets in the habitable zone, this Goldilocks region where there might be liquid water. And so these are worlds that could be like our own. One of the things that we're, all right, is this playing? No, it's not playing. Okay. One of the things that we have learned by virtue of having more than one example is that not all planetary systems are made the same. And by studying the dynamics of these multiple planetary bodies, we understand a lot more about how our solar system may have been created and whether or not there might be others out there like ours. We are getting closer to finding an Earth analog, Earth 2.0, an Earth-sized, then hopefully Earth mass planet in an orbit around a sun-like star where there would be the appropriate surface temperature for liquid water. And certainly with the detection of Alpha Centauri b, our nearest neighbor, we're really getting intrigued by the question of whether or not we can go there. If we find Earth 2.0, if it's nearby, can we go there? And so I work with a group called the 100-Year Starship Study, trying to pull together over the next century a focused program to perhaps understand the physics and develop the technology that will allow us to go to the stars. And in the process of solving these technological challenges for a Starship mission, have an enormous impact and benefit and feat on the planet that will have a beneficial effect to all of those that stay behind. And of course, once we find Earth 2.0, the second question is, does anyone live there? And although microbes and the search for biosignatures are a very robust field, we don't have the technology in place right now, and it's probably a couple of decades off. So for the next couple of decades, the only way to answer This does anyone live there question is SETI. It's the only game in town. And SETI, the search for extraterrestrial intelligence, which was really a search for extraterrestrial technology, began using radio telescopes, the product of radar technology development in World War II, and more recently, we've begun using optical telescopes. And what we're looking for is some extraterrestrial technology that's modifying its environment in ways that we can search over and be sensitive to over interstellar distances. So the Earth radiates at optical and radio wavelengths in many different ways for many different reasons. We are detectable at a distance. Perhaps their technology will be detectable by our own primitive technology. And whether or not SETI succeeds is totally dependent on how long, in general, technologies survive, right? If technologies flourish for a short time and then extinguish themselves or get turned off for whatever reason, then SETI will never succeed. Because there will never be two technological civilizations lined up in space, the here, and co-temporal in the 10 billion year history of our galaxy, the now, so they overlap and can be detected. But if SETI were to succeed, it would have an amazing, amazing story to tell us. Philip Morrison pointed out that due to the tyranny of light speed, SETI can be considered the archaeology of the future. Archaeology because any information contained in a signal would be telling us about their past, because the signal's taken a while to get here. But it tells us about our future, the fact that in fact we can have a long future. Someone else made it, we can as well. And so we've been doing SETI for a little more than 50 years with technologies that were developed primarily for astronomy. And in that 50 years, if you equate numerically the search space to the oceans on this planet, we've so far sampled 1 8-ounce glass. So when people say to me, "Oh, you've looked for 50 years, haven't found anything, must be nobody's there," I try and make this analogy. If you were looking for fish, if you wanted to know the question, are there any fish in the ocean? And you scooped 1 glass of the ocean and looked for fish, that's an experiment that could work, right? You could fit some fish in that glass. But the fact that you didn't find any fish after scooping 1 glass probably doesn't mean there are no fish. It means you haven't yet searched enough. And that's one of the great things about right now, right here, right now, is that technologies are allowing us to expand our searches exponentially, and exponents are incredibly powerful. So in the next decade or two, in fact, our searching can become significant. And here's a telescope we've built in Northern California precisely for doing radio astronomy and SETI research in a way that's far more powerful and efficient than we've been able to do in the past. So with our optical searches today, we can look for bright, very short nanosecond flashes of light. That would be the kind of thing that was generated by the petawatt lasers at Lawrence Livermore Lab, focused in by a 10-meter telescope. We could detect those out to 1,000 light years. Huge distance, 1,000 light years, 1% of the way across the galaxy we live in. All right, but that 1,000 light years is a lot farther away from home than we've ever been. And as well with our radio searches, we could detect our strongest transmitter, the radar associated with the Large Radio Telescope in Arecibo, Puerto Rico. We could detect that if it were 1,000 light years away and pointed in our direction. And so what does that 1,000 light years mean? Well, it's about 1 million stars like the sun. And if we were to have any chance of success in the next decade, which is when we can begin to have completed a search of those million stars, it would mean that technological civilizations had to, on average, last about 100,000 years. Not impossible, right? Very powerful lesson from a detection, even with no information content. And so I think SETI is incredibly important for our future, for an investment in having a long future. And a success would tell us that it is possible to survive. It's not going to provide extraterrestrial salvation. This is not a religion. But it will tell us that it is possible to become an old technology. And as a very young technology in an old galaxy, I'm not sure of how many other ways we can learn that. So I think it's important to get the world involved in SETI because the process holds up a mirror to all of us on this planet and shows us all as one. It trivializes the differences among humans. It trivializes the differences among nation states. And perhaps sets the stage for finding some way for us to develop the global governance that we've already heard today is going to be necessary for our long future. Thank you.